Okay, so you're involved in the CTC 145 course, and this is our advanced laboratory technique, right? And because it's an advanced laboratory technique, we want you to do some stuff on your own and not rely on us every single day. At the same time, the way that the laboratory is structured, you're going to be working on your own lab probably at any given point throughout the time, and that lab is going to be different than someone else's. So, the basic of the story here is for me to tell you that no solutions are going to be made. I'm sorry, you're going to have to make your own solutions for the lab whenever you need them. And one of the problems that people typically hit in the very beginning, even though they've seen these types of problems over and over in a general chemistry course, is the molarity formula. Yeah, that molarity formula was one of the most important things for you to learn in General Chemistry 1 and General Chemistry 2, and hopefully you'll remember some of the stuff about the molarity formula because we're going to be using it over and over. And you know, working in a laboratory environment, this is a number I've got to be comfortable with, right? I've got to be able to pop out this molarity equation, quickly solve a problem using the molarity formula, and that way I can make solutions in the laboratory as they're needed. So this video is just going to walk you through the steps of molarity, and really because this textbook that we're using in the summer course uses a lot of millimolarity or millimolar solutions, right? So I want to talk a little bit about that too. There's not too much of a difference. There's just one extra step involved, but I at least want to touch base with what that little bitty m out in front means. Okay, so just a quick recap and a quick review. Molarity is equal to the number of moles of substance divided by the liter. That is the equation that we use all the time for molarity, and that's what I would like for you to start out using, right? No shortcuts involved. I want you to understand what this equation is because shortcuts will get you in trouble. And if you remember molarity a different way and try to bring in more conversions, it's going to confuse the crap out of you. So I want you to at least be able to regurgitate that equation that you're seeing on the screen. Molarity equals moles divided by liter. All right, now I'm going to come over to the side and I'm just going to say that this is concentration. That's all that this is, right? So imagine that you go to the bar and you order a drink, and the bartender brings you the drink back and you sip it. And you squinch and pucker your lips and you say, whoa, that's strong, right? Well, that molarity is very high. The molarity of the alcohol is very high in that drink, so the concentration of the alcohol is very high. Well, if they bring you the drink back and you take a sip of it and it just tastes like mixers, then you're probably saying, well, where's the alcohol that I paid for in this, right? And I'm not encouraging you to drink by all means, but I know that probably most of you are doing it already. So if the drink comes back with all mixers and not enough alcohol, the molarity is going to be very low in regards to the alcohol, right? So that's all that molarity is. It's just a concentration unit. How strong or how weak is a solution? All right, now the key here is this thing called moles. And I want to come down here and talk about moles just for a second. So, moles. What is a mole? It's not one of those little creatures that bury underneath the earth, right? Mole in chemistry is something completely different. And a mole represents a certain amount. An amount of substance. The way that I want you to think about mole is I want you to think about the word dozen. Whenever someone says, I need a dozen of eggs, what happens? You automatically think of an amount. You automatically think of 12. And it could be a dozen of eggs, or a dozen of cats, or a dozen of papers, or a dozen of laboratory assignments. Dozen means the same no matter what it's referring to, right? This is a representative word that means an amount no matter what you're talking about. Mole is very similar. When I think of mole, in a laboratory environment or as a trained laboratory personnel or an entry-level chemist, I should automatically think of a number. But that number's not 12, right? A dozen is 12. A mole in chemistry is Avogadro's number, not avocado's number. You would not believe how many people say avocado instead of Avogadro. Don't ask me why, but they do. All right, so mole is 6.022 times 10 to the 23rd. And I'm going to put atoms back here, or I'm going to put molecules, depending on what you're talking about, right? If we're just talking about, let's say, just copper straight from the periodic table, or just oxygen, or just carbon, or just magnesium straight from the table, we're talking about atoms here most of the time. Molecules are typically compounds, and this would be like molecules of water, H2O, or molecules of salt, sodium chloride. And most of the time in a lab, we're going to be working with molecules here, but this also goes for atoms as well, and I never want you to forget that. That's always very important. All right, so 1 mole is equal to 6.022 times 10 to the 23rd molecules. Now that's half of the story, right? But 1 mole is also equal to the formula weight of the compound. And if you need a review on formula weight, then that is done in another video that is uploaded for Blackboard for your review. So in this video, I'm going to assume that you know how to calculate formula weight. All right, so 1 mole is equivalent to either one of these. If I need to get the actual number of atoms or molecules, I'll use Avogadro's number. And if I need to get the grams of stuff that I need to weigh out, and that's typically what I would do in a laboratory, I would use the formula weight of the compound. So Avogadro, right here, Avogadro's number. So the formula weight is what I would be using most of the time throughout the semester. All right, so let's take an example problem and just kind of quickly go through what these types of questions would look like. Let's say that you need to prepare 50 milliliters of a 0.250 molarity solution of sodium chloride. How much should you use to make the solution? You're going to see these types of problems scattered throughout the entire semester. So we need to get used to this calculation. All right, well, like I told you before, always start with the molarity formula. Molarity equals moles divided by liter. Well, the molarity I know, right? The molarity is given to me in the problem. And it says molarity is 0.250. So that's good to go. That's going to be easy for us. Next, what other thing do I need? Well, this is 50 milliliters. This is telling me how much that I need to make. And in this equation, I see liter that's involved. So I just got to remember to convert that number to liter, and I have the volume that I need to use, right? We don't want to be wasteful. We don't want to make a liter of solution every single time we've got to do something. So the volume is going to kind of restrict me, and that prevents a lot of waste. The only issue is that I have to recalculate to see what kind of an amount that I need to use to make that solution with. All right, well, from this point, the only thing that I have to do is come down here to the bottom. I know that the big M is molarity, and the problem gives that to me. 0.250 is equal to the little bitty m, which is moles. And then down below is liter. All right, well, 50 mils. To convert that to liter, milli means 1,000. So I need to divide by 1,000. So 50 divided by 1,000, right? If this was 0.5, that is 500 milliliter, right? That's not right. So 0.050 would be 50 mils. All right, now this is when the calculator will come in and be very friendly to me, as long as my batteries work. And I'm going to solve for the little bitty m up at the top, and that little m stands for moles, right? Not molarity. Capital M stands for molarity. So the way that I solve this problem is just like any other algebra problem. You need to make a math teacher happy here. And I'm going to take 0.050 and I'm going to multiply each side of the equation by that number. So I'm going to take 0.250 and I'm going to multiply 0.050 to that, and that will give me my little m, which stands for moles. So 0.05 times 0.250 is going to be 0.0125 moles, right? Now, here's the key. It's moles. And I don't have a balance that weighs out moles, right? This is the word kind of like dozen. I don't have a balance that can weigh out dozens of stuff, because depending on the stuff, they might weigh different, right? A dozen of eggs are going to weigh completely different than a dozen of pencils. So because of that, we have to get to a unit that's quantifiable, that I can actually measure and that I can actually do in a laboratory environment. So when it says, describe how you would prepare this solution, you're not going to stop here. You're not going to say, I'm going to take 0.0125 moles and dissolve it in 50 mils of water. No, that's not what you do. No one's going to weigh out moles for you. No one's going to do that calculation for you. You've got to do it. So from this point, I need to use some common sense a little bit and say I need to get to grams. So how on earth do I need to get to grams of the substance, right? Okay, well, what we decide to do, or what we do in this kind of situation, is that we take our moles, and in order to get to grams, so moles are here, and in order to get to grams, I need to use the formula weight. The formula weight of the substance that I am measuring or that I am using. So that means we need the formula weight here of sodium chloride, because that's what the problem tells me that I'm using. All right, well, over here to the side, sodium chloride. Sodium is 22.99. Chlorine is 35.45. There's only one each of each one of these, so I'm going to add these two things together, and 22.99 plus 35.45 is going to be 58.44. And the formula weight unit says gram per mole. Look at that, gram per mole. That unit's pretty important. All right, so I'm going to clear this out. 0.0125. I want you to remember that number because we're getting ready to use it again. And I have 0.0125 moles of sodium chloride. Right, and I'm going to set up a dimensional analysis problem. I'm going to put that over 1. Then I'm going to bring in another step. Well, the way that you do dimensional analysis is that the step on top needs to go on the bottom in the very next step, right? So moles of sodium chloride, I need moles of sodium chloride down here, and I need to go to grams of sodium chloride. And that way these units can cancel each other out. That's the whole purpose of doing that, right? Well, just a while ago, we had a magic number, and that magic number was 58.44 grams per mole. That was the formula weight for sodium chloride. Well, look at this. Gram. And in my conversion unit, there's my gram. So it's 58.44 grams. So 58.44 grams of sodium chloride for every 1 mole of stuff. Well, here's my mole, and I'm going to put a 1 there. So basically what I do is that I take the moles that I saw for in the molarity, and I multiply by the formula weight. That's what we're doing right here. 0.0125 times 58.44. And we're going to divide that by 1 times 1, which is 1. So same number no matter what. So 58.44 times 0.0125 is going to be 0.7305 grams. So that's how many grams I would weigh out of sodium chloride. And then I would take that number of grams, I would put it in a volumetric flask, and I would dilute to the line, right? So here is my volumetric flask. I would take the solid, put it in the volumetric flask. Solid's going to be down here in the bottom. Then I add a little bit of solvent, probably water, shake it up, make sure that it dissolves, and then I take it on up to the line in the volumetric flask where the 50 ml mark is etched. And that is how I've made my solution. Okay? So, a couple of things to remember here. Molarity formula. Molarity equals moles divided by liter. Almost every single time in this semester doing these labs, you will have a molarity that you will need to make, and you will have a volume that you will need to make. This means that you will be solving for the number of moles. Once you get the number of moles, you'll then multiply by formula weight of the compound, and that will give you grams that you need to use to make your solution. All right? So in the beginning, it might be a little tricky. You might have to refer to your notes. You might have to walk yourself through the calculation. But hopefully at the end of the semester, this calculation will become so natural that you will be able to do these and not think about them once. Because that's your job working in a laboratory, is to make solutions. And that's why they pay you the money that they pay, because you know how to do it. And a lot of other people don't. Now, one last thing before I stop this video, and that's this issue of millimolar. This lab loves millimolar. For some reason, when they write these experiments, and it's probably due to the low concentrations that they are using in some of them, they convert these things over to millimolar, and I don't want you to be confused with that. You treat millimolar the same as you treat molarity. No difference. Millimolarity or molarity. There's just one extra step. So let's say that you are required to do a 50 millimolar solution of the salt maybe that we just did. The step that you have to do extra is in the very beginning. Now, note, molarity is equal to moles over liter, right? This is molarity. This is not millimolarity. Milli means 1,000th of. Millennium, 1,000, right? So I need to convert this number over to molarity first. And then when I get that, I can then plug that number into the equation and solve it just like I did before with no other issues at all. So that means I need to get the millimolarities and I need to convert them to molarities in order for these equations to work. Okay, milli means 1,000, right? So over here to the side, I'm going to just do a quick conversion, and I'm going to do it on kind of the proper way of dimensional analysis so you can see how this is going to work. 50 millimolars over 1. All right, so in the next step, I do a multiply, do my dividing line just like I did up here at the top, and millimolar is on top in the first step. So millimolar goes on the bottom in the second step. And I need to convert that over to molarity. So millimolarity, convert it to molarity. Milli means 1,000, right? That's my conversion unit that I need to remember. So there are 1,000 millimolarities in 1 molarity. Doesn't matter what the unit is. Milli always means 1,000. All right, so that's my proper unit. So I'm going to take 50 times 1, which is 50. And then I'm going to do 1 times 1,000, which is 1,000. So my answer here at the very end says I need to take 50 and I need to divide it by 1,000. And if I do that, I'm going to get 0.05. That is the number that I now use in the actual molarity problem, right? So 50 millimolar is equal to 0.050 molarity. I just added the extra 0 on there, right? That's all I did. Same number. So this is the number that I will then use in my molarity equation in order to solve for how many grams I need to weigh out to make that solution. So, shortcut, I take millimolarities and I divide them by 1,000 every time. And that will give me the molarity that I need to use in the equation. All right, so hopefully that will be a start of you on the right track to start solving these problems the proper way when it concerns molarity calculations. Okay? So molarity formula is very important. Solving the molarity formula is very important to get mole. Using the formula weight to convert mole into actual grams that you can weigh out is very important. And understanding what millimolar or millimolarity is all about is also important for this particular course, because that's the way the labs are written. Okay, so that's it of molarity. Hopefully this will be okay for you, and you're probably going to see other videos concerning calculations and solution preparation for this summer as well, located in the same area. And if you need reviews on those, you're more than welcome to watch them, to take some notes, and play around with the calculations. In the laboratory, if you are doing these for the first time and you are unsure if you're going to be making the solution the proper way, let us look at your numbers. We will look at your calculation. We'll make sure that you're doing it the right way. And if so, we'll give you a check and we'll tell you, good job, go make your solution. We're not going to get angry, right? You're not going to be graded on did you make the solution the right way. So ask us about it, right? We're interested in your final products for these laboratories, not the process of how you're getting to that point. Meaning that if you're messing up calculations, we're not going to take points off as long as we catch it and fix it before you give us the products at the very end. So don't be a stranger. We're not going to bite.